Since we're going to talk about the exponential functions, let's begin by talking about a couple of properties of exponential statements or expressions. To the left here, I have one of the properties of exponents. There's several, but these are the two that we're going to be using in this section and going forward. So the first one is the rewrite of a rational exponent as a radical. So this is the relationship between radical expressions and rational exponents. And the one to the right is the negative exponent rule. You may recognize both of these because we've talked about these before. Now, to give you an example of, for example, the negative exponent rule, suppose I have an expression like this, 3 to negative 2, and we want to know what this number is. So using the negative exponent rule, I can write this as, or rewrite it as its reciprocal with a positive exponent. Now, once we have positive exponent on the base, 3 squared, then we can translate that as a repeated multiplication of 3 times 3, and the result is going to be 1/9. So the answer to 3 to negative 2 is going to be 1/9. Okay, now what if I want to do expression like this? Suppose I have 27 to 2/3. To understand expressions like this, now we're going to use the radical version of it. The denominator in the fraction appears as the index of the radical, so that's going to be 3, which we call the cube root, and the base is going to become the radicand. The exponent could go on the outside, which is the numerator in the fraction. Cube root of 27 is 3, and 3 squared is 9. So this would be, again, a way to rewrite rational exponents. What if I have something like 16 to negative 1/2? For this one, I have both negative exponent and a rational. So let's see. First, to deal with negative exponents, I'm going to rewrite it as such. And then 16 to 1/2, using the radical expression, that would be square root of 16. Now let me show you a little detail on this one. So remember, the denominator becomes the index, the base is the radicand, and the exponent is the numerator. But in the case of exponent 1/2, what we don't see is 1 and 2 here in the general form. Like you can see down here, I have just square root of 16. It's like, what happened to 1 and 2? Well, 2 becomes the index. If the index of the radical is 2, we simply call that the square root, right? There. And if the exponent is 1, we simply don't write it. So that's why 16 to 1/2, which is the way I have it, it's written as a square root of 16, which of course the answer is 4. So this is going to be 1/4. Okay, perfect. Now we are in a position to actually talk about exponential functions. So an exponential function, here's my statement. The exponential function is any function that can be written in the form f of x is equal to a to the x, where a must be, the base must be positive, and it cannot be 1. Now the reason it cannot be 1 is simple, because 1 to the x power is 1, and in this case you simply get a flat line at 1. There. That's not an exponential function. Okay, there you go. That's just a constant function at 1. That's the reason a cannot be 1. The reason a has to be positive is for this reason. If I let, for example, let a be negative 3, I'm letting it to be negative number. And if I have negative 3 to 1/2, then I can rewrite this using the radical form as the square root of negative 3. Now, square root of negative 3 is not real because the radicand is negative. A number times itself, a real number times itself, cannot equal to negative. So this is not real. Therefore, the restriction for a to be positive. Of course, if I have something like -3 to 1/3, that one would be okay, but we don't want to make exceptions for, let's say, fractions whose denominators are even or odd. Okay, so in general, we're just going to say that a has to be positive. All right. Now, what is this thing going to look like? To begin with, we're just going to plot points. Let's say, for example, I want to know what the graph of this function 2 to the x qualifies as an exponential function, and let's say we want to graph this function. Well, we can plot points, right? Anytime we work with a new function, it's always good to plot points and see how the function behaves. So I'm going to pick maybe 5 points on the graph of this function. And then we're going to plug them into the function. So the case where x is -2, I have 2 to -2 using negative exponent rule. That's just going to be 1/4, right? So here we have 1/4. And if it's -1, 2 to -1 is going to be 1/2. That's 1/2. 2 to 0 is 1. So that's going to be 1. 2 to the first power is 2. 2 squared is 4. Okay. So once I have this, now I can actually graph this exponential function. Just a rough sketch. I'll do better graphs of these using Desmos in just a few minutes. But for now, it suffices to just graph these. And when I plot points, I'm going to get something like this. I'm going to now superimpose the points on top of these. So this point, and then let's say this point. Call this -1, -2, and this would be like 1 and 2, like so. And there we have the points. So that's going to be 2, 4. 1, 2 is going to be this point, and so on and so forth. Okay. So if you connect the dots, connect the points, and you're going to get a general graph that looks like this. Now we can make a number of observations, by the way, from this simple exponential function. Let's write down as much information as we can about this function. The x-intercept, the graph of 2 to the x will not have an intercept, and here's why. X-intercept, that is. Remember, if hypothetically, if this function was to graph the x-intercept at some point here, okay, at that point y would be 0. And then it begs the question, 2 to what power is 0? And notice here we pick some points to try out. For example, when we picked x to be 0, 2 to 0 is not 0. 2 to 0 is 1. And judging from positive numbers that I picked, it seems like no matter what I pick, the answer cannot be 0. So 2 to the x therefore cannot be 0. Now the fact that it cannot be 0 means that the graph will not cross the x-axis. As a result, because it can't be 0, there is no x-intercept of the graph. Okay, there's no x-intercept of the graph. There is a y-intercept, right? At when x is 0, y is 1. So let's write this information. The y-intercept is going to be at 0, 1. The x-intercept, we said, there is none. In fact, the x-axis serves as a floor under the graph of the function. The function does not breach or break that floor, touch nor cross it. Okay, and this floor here, the x-axis in this case, is called an asymptote. X-axis is what we call a horizontal asymptote. Okay, we talked about these before when we graphed polynomial rational function. Remember, we talked about horizontal, vertical, slant asymptotes. So that's what this is. It's a horizontal asymptote of the graph. What else? The domain and range is always good to know. What can I plug in into exponential function? Anything, right? And what is the range? Well, the range, because it cannot cross the x-axis or touch it. Therefore, the function is always above the x-axis. So it's a positive function, 0 to infinity. And the function is always increasing as you move from left to right, increasing over the entire domain. And you can see that, for example, you see it's always rising like that. Increasing. So we talked about domain, range, and all the key points. And lastly, if you do the horizontal line test, it passes the horizontal line test. Which, remember, the implication of that in the previous section was that if the graph of a function passes a horizontal line test, that means the function is 1 to 1. And again, direct implication of that is if a function is 1 to 1, therefore it has an inverse. So it is possible to establish two-way communication using exponential models. Right? And there you have it. So this is, again, general information about the graph of f of x equal 2 to the x. Now, if this was 3 to the x, 4 to the x, in fact, any base greater than 1, all of this information would still work. Okay, what I have here works for as long as the base is greater than 1. Now, let's take a look at another example. This next example, I'm going to do g of x. And this time we're going to go 1/2 x. So my base is now less than 1. Still positive, but less than 1. Now, 1/2 to the x is the same as 2 to negative x. The property we use here or cite here is a over b to m equals b over a to negative m. So you can flip the fraction, change the sign in the exponent. 1/2 becomes 2 over 1, x becomes negative x. All right, so how are we going to graph this one? And if we plot points for x and y, I'm going to go with the same 5 points we had earlier. Let's see how this is going to work out now. Okay, when it's -2, and remember I'm going to look at this version instead of 1/2 to the x. So I'm going to go 2 to -2. Oh, I'm sorry, -2 to the power of -2, which is going to be 1 over -2 to the square. Notice I'm putting parentheses around -2. If I don't, I will not get the correct answer. Because x is a negative value, so I'm going to contain that negative value, preserve it using parentheses. So that's going to be -2 squared. -2 times -2 is 4, so that's going to be 1/4. When x is -1, -1 to -1 power, that's the same as -2 to -1 power is the same as 1 over -2 to first power. That's just -1/2. Right? Okay, let's see. Okay, I'm doing, hold on. So sorry. The base is 2, right? The x is -2. I confuse myself. Base is 2 to -2. The answer doesn't change, luckily, but I just didn't have it correctly. So this is actually going to be 4. Yeah, the answer did change there. Okay, when x is -1, not the base, x is -1. So that's 2 minus -1. That's going to be 2 to the first. So that's just 2. When it's 0, that's the easy case. That's 1. When it's 1, I have 2 to -1, and that's 1/2. There you go. Now that's negative exponent. When x is 2, you get 2 to -2. That's 1/4. And there you have it. So the numbers work out fine. Now, what does the graph of this thing looks like? Again, if I plot these points, here's x, and there's the y-axis. This time, it turns out that the function looks like this. So this point, again, would be 1, 0, 1, that is. And then these other points, there you go. These other points would be the ones that are, for example, this would be 1, and this would be 2, That's 2 and 1/4. This was 1 and 1/2, and so forth. At this point, let's call that point the high point. This point is -2, 4, let's say. Okay. So again, connecting the dots will give me something like this. I promise I'll do actually better graphs of these in just a moment. I'm going to go to Desmos and actually show you the behavior of this function for different values of a. Now, one thing that's interesting about this function, 1/2 to the x, which became 2 to negative x, it looks like this function, now let me graph it this way. Okay, call this 1/2 to the x, which became 2 to negative x. Looks like that is actually a reflection of this function, which is 2 to the x, right? About the y-axis, right? If you flip it about the y-axis, that's what you get. So we can see, therefore, the effect of negative in the exponent here. The effect of negative is to cause a reflection of 2 to the x about the y-axis, and that's no surprise. Remember, back in chapter 3, we mentioned if we have, let's say, a function g of x, which is f of ax in parentheses, which is exactly what this is. My, let's say, g of x in this case is f at negative x of, where f of x is a to the x. And if this number a, so here a is -1. A is -1. If this number is less than 0, then we have a reflection across the y-axis. So my point is that what we're seeing is consistent with what we talked about in chapter 3 as far as the effect of these numbers on the original function, in terms of transformation of the original function, that is. Okay. And there we have it. So we have the graph of this. So let's actually go to Desmos. I have Desmos running here, and you can see what this is going to look like. Let me maximize this window there. And well, let's take a look at the graph of Desmos here. So what I've done here, actually, I have this function a to the x in general, and then I'm going to allow a, the base, change within the valid values, right? Remember, a has to be positive, so I'm starting at 0.1. I'm going to 3. You can go to infinity, but this will do. Right now, a is at 0.9, and look at the direction of this function, this exponential function. See what it looks like there. That's at 8.9. Okay. As the number changes, let me now do this. You can see how the exponential function behave. And let me actually slow this down a little bit. It's going too fast. There. So you can look at the variable values of the base. The base, for example, let me start it at 1, we get a flat line, right? So if I move this, you see here, 0.9, 1.1, how it toggles back and forth. It's actually being reflected. Let me show you the rest of this graph also. It's gonna, oops, sorry, didn't want to do that. Okay, there you go. That's the rest of the graph. So I'm just gonna go between 0.9 and 1.1. See that, how it reflects? Like that. Now, as the number increases, you see how it rises because the base is increasing. The base is increasing. So now I'm going to let it play and you can see what happens. There we go. So it becomes steeper, and it looks like as if it's touching the x-axis, right? The function, but it really isn't touching the x-axis, although it seems that way. But it's gets so close to it that's visually it's very difficult to see. Now look at this part, for instance. This is when the graph, but the base is 0.3 between 0 and 1. Look at this one, 0.1, 0.3, 0.5. So as long as the base is less than 1, look at the shape of this graph. It's decreasing, right? And then it switches to become increasing. Now it's increasing. For values of base greater than 1, it rises as you go from left to right. For less than 1, it actually falls as you go from left to right. Okay, and we'll see that again in a moment. And then I'll go back to my note. So there you have it. You see this? The value is decreasing. And in all cases, it will go through 0.01. That's this point right here on the y-axis. So there you have it. You can easily graph this one again. I'm using Desmos for this. All right. Now, having talked about this, let's generalize now the effect of base on the general exponential function. In general, we said if I have the function whose base is greater than 1, the function is going to be rising. So that's going to be the general exponential function. And all exponential functions, before you actually move them, use transformation, they all go through 0, 1. All of them do. All right, so this is a case where a is greater than 1 now. Okay, and so the graph is a to the x. If it's greater than 1, and the case where a is between 0 and 1, the exponential function is going to behave like this. There. This is going to be a between 0 and 1. And remember, a cannot be negative. So that's pretty much covers it. And a cannot be 1. At 1, you get a flat line, horizontal line, which we don't want. And there you have it. Now, one of the properties, by the way, of the exponential function is what we call the one-to-one property, because the function is one-to-one. So let's talk about the one-to-one property. One property of exponential functions. And the one-to-one property says that if you have a to the x is equal to a to the y, therefore x and y must be the same. Okay. So this is also known as the principle of exponential equality. And this actually can enable us to solve equations, although it's simple, but very useful. So for example, let's say I have an exponential equation. This is exponential equation because the variable x is in the exponent. Okay, so for this one, I can rewrite 4 as 2 squared to the x equal to the right side. I'm just going to write 2 as 2 to the first. So this now becomes 2 squared is 4. Right, oh, I don't want to go back, sorry. Oh, another property of exponents we have, if we have a to the m to the power of n, remember, this is the power of the power rule we're going to apply. We can actually multiply the powers, the exponents. So m and n will multiply. Therefore, the left side becomes 2 to 2x, and the right side remains as 2 to the first. Now I can apply the principle of exponential equality to this one, right? And according to that principle, the bases are the same, exponents must be the same. So I'm going to say 2x is equal to 1, and then we can easily solve for x there. So x must be 1/2. And there's the answer to this one. Very handy property. Let's look at another example. Let's say in this example, suppose I have the number e. E is approximately 2.718. It's an irrational number, just like pi is. So suppose I have the number e, and the base of my exponential function is e now. And I have e to the 4x minus 1 is equal to e squared to the x. And I want to solve this equation. Remember, the key to use the one-to-one property is to have common bases, which we can see a common ace of e emerging out of this one. I can rewrite the right side using the power rule of exponents as e to 2x. And now I can equate the exponents because the bases are common. So this would imply 4x minus 1 is equal to 2x. And again, we can easily solve these, right? Subtract 2x from both sides, add 1, divide by 2, and I just so coincidentally got a half again. All right. Let's take a look at another exponential equation. In this example, suppose I have 27 to 4x equal to 9 to x plus 1 now. Remember, we need to have common bases, and we don't at the moment. The common base between 9 and 27 would be 3. So 27, I can write it in base 3 as 3 cubed, right? And 9 in base 3 is 3 squared. X plus 1 is the exponent. And then I can apply the power rule. 3 times 4, the exponent on the left side becomes 12x. And on the right side, I have 2 times x plus 1. All right, now we do have common base. Therefore, we could equate the exponents. As a result, 12x is equal to 2x plus 2. I went ahead and distributed. Subtract 2x and divide by 10. So x turns out to be 1/5. And there you have that one. Well, let's look at a couple of more examples of these exponential equations. What if I have x to 2/3 is equal to 4? Okay, well, x to 2/3. Let's see, I can rewrite this in radical form, couldn't I? That would be cube root of x and then squared, correct? And 4 is 2 squared. And again, due to the one-to-one property, we have same exponents, therefore bases must be equal. So I can set cube root of x is equal to the base, which is 2. Now cube both sides, x becomes 2 cubed or 8. And there we have it. The answer to x is 8. In other words, if you do 8 to 2/3, which means cube root of 8 squared, we get 2 squared, we get 4, which is the right side. All right, so this, we can call this one a check. We just check this solution. You can always check the answers by plugging them in, correct? The reason I don't, because I'm comfortable the way I'm doing this, and that because there's no restriction on domain of exponential function. They can handle all real numbers. So that's why I didn't check my solutions earlier. Let's take a look at one last equation here. Suppose this time I'm going to make a negative exponent. That's equal to 1/64. Well, the negative exponent, I can write it as 1/x to the 6 equal 1/64. Now this time I have a fraction. For these to be equal, because the top is the same, 1 and 1, the bottom must be exactly the same, right? So x to the 6 should equal to 64 for these to be equal. Same fraction. And I want to solve this one. I can rewrite 64 in base 2 as 2 to the 6th. Again, I have a case where exponents are the same, bases must be the same. So x has to be 2 in this case. All right. And let's wrap this up with, I just want to do one graph of this kind. Suppose I have, I want to graph this function, f of x equals 1/3 2 negative x. So it is an exponential function. The exponent is negative, right? So what I'm going to do is I'm just going to change this to a positive exponent. And that's just 3 to the x, isn't it? And we know what the general graph, if base is greater than 1, gonna look like. And there you go. That'll be the graph of this function. See how quickly I can graph them? I didn't plot any points. We could, so I'm looking at the general shape here. Okay. You can plot points specifically like on a grid and get more accurate graph, but I'm looking at the general graphs. So that's all we wanted to do in this section. We just wanted to introduce the idea of exponential functions and be able to graph these functions either with software or by hand. So with that, we can conclude this lecture now. Thank you for watching.